This is the first in a series of videos about the equilibrium constant, K. We are going to talk about what the formula for K is, the difference between Kc and Kp, how to combine different K values or to manipulate them, and what the size of that number for K really means. So as we talked about in the last video, we know that the equilibrium constant represents the point where the rates of reaction of the forward and reverse reactions are the same, but we don't know about the concentrations. And we really want to know about concentration. So this is where the equilibrium constant comes in. It represents how much of each species or substance is present at equilibrium. We can really get a feel for what that solution looks like. Okay, so let's use a generic reaction here to indicate how we would write this constant, and we'll use our new favorite double-sided arrow. So we're going to have reactant A plus reactant B goes to product C and product D. M, N, X, and Y are the coefficients in this case. So our equilibrium constant K is going to be the concentration of products divided by concentration of reactants. And in that way, the products indicate, the amount of product indicate how far the forward reaction proceeds, and the amount of reactant indicates how far the reverse reaction proceeds. So we can write that as concentration of C times concentration of D, which are the products, over the concentration of A times concentration of B. And there's one more thing we need to include. We need to include these stoichiometric coefficients from the balanced reaction as superscripts for each of these concentration terms. Oops. Let's circle that in red to make sure we don't forget. So those stoichiometric coefficients are going to become superscripts in our expression. So don't forget those. They're important. They can make a big difference, as in this example. So here's a real chemical equation between the dimer, N2O4, in equilibrium with its monomer, NO2. Both of them gases. So if we wanted to write the equilibrium expression for this, we would write products over reactants. So NO2 is our product, N2O4 is our reactant, and then we'll go back and add in our superscripts, 2 for NO2 and just 1 for N2O4. So you can write 1 or you can just leave it blank. Either is fine. Okay, so this is pretty straightforward except for remembering to do the superscripts, but we'll practice. But now it's time for our stop sign, because we can't just stop here. There are a few more conditions to consider before we continue. There are some species that we don't include in these expressions. And the reasoning is a bit more advanced than we are really prepared to talk about. Suffice it to say that the concentration ratio is an approximation. The real expression for K is something called activity, and activity relates to whether something changes. And there are some types of things that don't change. So pure liquids and solids, pure liquids, pure solids, and solvents. These are the kind of things that we don't include in our expression. And that is because their concentrations don't change by an appreciable amount. If we were to disturb this equilibrium and push it to one side or the other, the shift back and forth would be pretty small. And if we have something like a solvent, which is 55 times greater than anything else in the solution, it is so much greater that a tiny change in concentration will not make a large effect. So that is the best explanation that I can give you at this point for why we leave those out. You'll just have to take my word for it after that. Okay, and then we're going to throw in one more example here before we get to that next header, which I have inappropriately placed there. So let's look at an equation with some of those pure solids and liquids in it. This one. So this is calcium carbonate at equilibrium with calcium oxide and carbon dioxide. Now this is not something that is going to happen at room temperature. This happens at 1200 degrees, very, very high temperature. So what happens is when we have some of that calcium carbonate at 1200 degrees in a sealed container, if we heat it, we can take some of the solid at the bottom of the container and we can break it down into a different kind of a solid and a few molecules of gas. And when we write the equilibrium expression, K, we are not going to include calcium carbonate or calcium oxide because these are pure solids and we leave them out. So the only thing we'll include is our CO2 that's a gas, and then there is no denominator, or you could say that the denominator is 1 because there's something in it. And this is because these solids, the concentration is so much larger than that of the gas that adding a little bit more solid is not going to have any effect on the gas up top. The only thing that affects the equilibrium is changing the amount of gas. And so since we talked about that, you're probably wondering, why are we talking about gas in terms of concentration? That's not the unit we usually use. Usually we use the value of pressure to measure gases. And so we should do that. Oh, here, let me add my summary sentence before we move on. Adding one of these solids or the other doesn't affect the concentration of carbon dioxide. Okay, now we can talk about Kc. So what we have shown so far has been Kc because we've used concentrations. So if you use concentrations to make your relationship for the equilibrium constant, you get Kc, K of concentrations. And if we're using pressure, we can write the equilibrium constant more appropriately for a gas. And so we'll call that the Kp, the equilibrium constant in terms of pressure. Looks like so. And I want to do it for the other one that we drew up here, just so you can see what it looks like with the subscript. All the same rules apply. So here we had NO2 squared over N2O4. And if we were to write it with pressure, we do the same thing. So the pressure of NO2 squared over the pressure of N2O4. So this is really nice because we can write it in terms of pressure for gases or in terms of concentration for liquids. However, these numbers, Kc and Kp, they are not going to be equal. Almost always, Kc does not equal Kp. So first of all, that means you definitely need to specify whether you're solving for Kc or Kp, because it really does make a difference. Second of all, we want to know how we can convert between these two numbers. So one way that we're already familiar with to convert between pressure and concentration is the ideal gas law. really connecting it back to our first chapter here. The ideal gas law is pressure times volume equals numbers of moles times the gas constant times temperature. And so we want to relate pressure to concentration. So let's rearrange that to solve for pressure. So pressure equals nRT over V. And I wrote it a little bit strangely because I wanted to emphasize that we have N over V. And you can probably recognize that moles over volume is molarity, also known as concentration. So this formula is going to help us relate concentration and pressure. So there is a bit of a derivation that goes into it, but you can read your book if you're interested. You can take this formula and substitute it in to the Kp expression. And we end up with Kp equals Kc times that RT bit at the end. And there's just going to be an exponent here. And that exponent is going to be the change in the number of moles of gas. Because pressure only makes a difference when we're talking about gases. Just to be clear, change in number of moles of gas is the number of moles of gas in the products minus the number of moles of gas in the reactants. So for example, in this one that we had up here, there were 2 moles of gas on the right side, 1 mole of gas on the left side. So the delta N gas would be 1 mole. So that was a lot of information. We learned how to write the expression for K. We learned what we should leave out. And we learned that there were 2 different versions, one with concentration and one with pressure. So let's quickly do an example just to make sure that the plug and chug steps are familiar to us. Okay, here's our example. So the example reaction is this ammonium compound that's a solid in equilibrium with ammonia gas and hydrogen sulfide gas at 295 Kelvin. And we have the partial pressures for each of the gas pieces, and we need to find Kp and Kc. So you can find these in either order. I always choose to start with the easiest one. Always take the lowest hanging fruit. So we're given the pressures. So that means that the Kp is the easiest to solve for. And if it's the easiest to solve for, I'm going to solve for it first. All right, so we're going to do Kp, which is products over reactants in terms of pressure. So we want to do pressure of the NH3 gas times the pressure of the H2S gas. And then in the denominator, we'll have the reactants, but this is a pure solid, and we'll leave that out. So we can just write 1, or we can just write nothing. So we leave out pure solid NH4HS. Okay, so we've got our expression, and it's always a good idea to write it generically in terms of the compound before you plug it in, just in case you make a math mistake. We can plug in our 0.265 atmospheres for each of these. And then you can plug that into your calculator. And so for Kp, we should end up with 0.0702 at 295 Kelvin. You'll see why in a little bit, but it is always important to report the temperature with your Kp value, because the K will vary with temperature. Another interesting thing, I wasn't just being lazy, there really is no unit for the K value, and that has to do with its more formal definition that has to do with activity rather than with concentration or pressure. But the real value of K with activity is unitless. It doesn't have a unit in it. And even though we're technically doing an approximation by using the pressure or the concentration, we'll honor the real way of doing it and report it without a unit. So your KP and your KC do not have a unit. So now we have KP and we want to find the other one, KC. So here's our formula that we wrote on the previous page. And we can plug these in. So here's the value we just found for KP, 0.0702. We're looking to find the KC. We can plug in our R constant, and we want to use this one, 0.0806, the one that's in atmosphere liter mole Kelvin. We always want to choose that one because this is the one we use for the gas law because it has a pressure unit in it. And we're going to multiply that by the temperature, 295 Kelvin. And then that entire term is going to be raised to the delta N gas molecules value, which is 2 molecules of gas in the product minus 0 molecules of gas in the reactant is 2. So with a bit of rearranging and input into your calculator, you should arrive at a value of 1.20 times 10 to the negative 4th for Kc, and that's at 295 Kelvin. Remember, we always include the temperature. We'll write that here just to be clear. Report the K value with its temperature. That's important. That gets a box. And this is an answer. So this gets a box. And again, our Kc doesn't have a unit because our K is always going to be unitless. So now we're familiar with how to use K, how to plug into the Kp and the Kc expressions and to convert between them. And the next video, we'll look at some more manipulations, how to combine more than one K value together.